Category O, Lecture 14, Tilting Modules. We start this lecture with a brief recollection of the theory of quasi-hereditary and stratified finite-dimensional algebras. Let K be an algebraically closed field and A a finite-dimensional associative K algebra. Let us enumerate simple A modules as L1, L2, and so on, Ln. Please note that in this way, we effectively have chosen a linear order on the set of simple modules. This will be an important part of the structure which we are going to discuss. So we denote by Pi the indecomposable projective cover of Li, and by II the indecomposable injective envelope of Li. Let us now define standard and proper standard modules. Recall that the trace of module X in module Y is the sum of images of all homomorphisms from X to Y. For each I, we define the standard module delta I as the quotient of the projective module Pi modulo the trace in this module Pi of the projectives Pi plus 1, Pi plus 2, and so on, Pn. Alternatively, one can say that the standard module delta I is the maximal quotient of Pi, which has the property that this quotient does not have as composition factors any Lj's for j strictly greater than I. Next, we define the proper standard module delta I overlined as the quotient of delta I modulo the trace of Pi in the radical of delta I. And the radical of delta I is a submodule of delta I, so this trace will be a submodule of delta I. Alternatively, we can say that the proper standard module delta I overlined is the maximal quotient of delta I, which has the property that the composition multiplicity of Li in delta I overlined is equal to 1. Please note that for these definitions, we crucially used our fixed order on simple modules. Next, let us define costandard and proper costandard modules. Recall that the cotrace of X in Y is the intersection of kernels of all homomorphisms from X to Y. Now we define the costandard module nabla I as a cotrace of the injective module II in the direct sum of the injective modules II plus 1, II plus 2, and so on, In. Alternatively, we can describe nabla I as the maximal submodule of II, which doesn't have any composition subquotients which are isomorphic to Lj for j greater than I. Next, we define the proper costandard module nabla I overlined as the full preimage in nabla I of the cotrace of the quotient of nabla I by its socle in II. Alternatively, the proper costandard module nabla I overlined can be defined as the maximal submodule of nabla I, which has the property that the simple Li appears only once as its composition subquotient. Again, note that for these definitions, we crucially used our fixed order on the simple modules. Now we are ready to define the notion of a standardly stratified algebra. Denote by f of delta the full subcategory of the category of A modules, which consists of all modules that have a filtration with standard subquotient. We say that an algebra A is standardly stratified, provided that the projective generator of A belongs to F delta. In other words, each projective A module has a filtration with standard subquotients. We denote by F nabla overline the full subcategory of A mod, which consists of all modules that have a filtration with proper costandard subquotients. There is a theorem, which is due to Agoston, Glab, and Lukács from 1998, which says that A is standardly stratified if and only if the injective cogenerator of A mod has a filtration with proper standard subquotients. The relevant literature for these notions is the memoirs paper of Klein, Partial, and Scott, which is called Stratified Endomorphism Algebras, and the paper of Agoston, Glab, and Lukács, which is called Stratified Algebras from 1998. Next, let us discuss properly stratified algebras. Denoted by F delta overlined, the full subcategory of A mod, which consists of all modules having a filtration with proper standard subquotients. And finally, denoted by F nabla, the full subcategory of A mod, which consists of all modules having a filtration with costandard subquotients. We will say that algebra A is properly stratified, provided that it is standardly stratified, and additionally, the projective generator of A belongs to F delta overlined. For example, any standardly stratified algebra having a simple preserving duality is properly stratified, because having a simple preserving duality in particular means that the algebra is isomorphic to its opposite algebra. Note that A is properly stratified if and only if the opposite algebra is properly stratified. However, for standardly stratified algebras, this later claim is not true. There are standardly stratified algebras such that the opposite algebra is not standardly stratified. Relevant literature for properly stratified algebras is the paper of Glab, which is called Properly Stratified Algebras from 2000. Now we can define the notion of quasi-hereditary algebras, which was the original notion. It was defined before stratified and properly stratified algebras. Stratified and properly stratified algebras are generalizations of quasi-hereditary algebras. But when you try to define them all, it is more natural to start with stratified algebras. So definition, A is called quasi-hereditary, provided that it's standardly stratified and all standard modules coincide with the corresponding proper standard modules. Alternatively, A is quasi-hereditary, provided that all proper costandard modules coincide with the corresponding costandard modules, and an injective cogenerator of A has a filtration by costandard modules. And an algebra A is quasi-hereditary if and only if the opposite algebra is quasi-hereditary. The terminology quasi-hereditary is motivated by the observation that an algebra A is hereditary if and only if it is quasi-hereditary for any choice of linear order on the set of simple modules. And the relevant literature is the paper by Glab and Ringel, which is called Quasi-Hereditary Algebras from 1989. Here are some examples. Consider the quiver as follows: two vertices 1 and 2, and two arrows alpha and beta, alpha from 1 to 2, beta from 2 to 1. And consider the quotient of the quiver algebra by the relation alpha beta is equal to 0. Then the indecomposable projectives for this algebra looks as follows. So the projective P1 has 1 on top, then 2 in the middle and 1 in the circle, and P2 has 2 on top and 1 in the circle. So in particular, if we look at standard modules, so 2 is greater than 1, we take the natural order. So the second projective is its standard module. And when we factor out everything below 2 in the first projective, we get that the simple L1 is a standard quotient of the projective P1. And then we see that both projectives have standard filtrations, and the standard modules are also proper standard, because the multiplicity of 2 here is 1 and the multiplicity of 1 here is 1. So this means that A is a quasi-hereditary algebra. Here's another example. We consider the same quiver, but now we factor out the relation beta alpha beta is equal to 0. Then the indecomposable projectives become bigger. So the second projective has 2 on top, 1 in the middle and 2 in the circle. And the unique Löwe filtration of the first projective starts from 1, then goes to 2, 1, and then 2 in the circle. Again, we must have that the projective module P2 must coincide with a standard module. And then if we factor out everything below any 2's in the first module, we get the simple L1 coincides with the standard module for 1. However, if you look at proper standard modules, so the proper standard module for 1 is the same as a standard module. However, for 2, we need to factor out everything below any non-top appearance of 2. The proper standard module for 2 will be 2, 1. And then we see that P2 doesn't have a filtration by proper standard modules. So this algebra B is standardly stratified because projective have standard filtrations, but it is not properly stratified. Let us now discuss the notion of highest weight categories. Let C be an abelian length category with enough projectives. Fix a linear order on the set of simple objects of C. So definition by Klein-Partial-Scott from 88, we say that C is a highest weight category, provided that for each simple L, there is a module, a standard object denoted delta L, such that the projective cover of L surjects onto delta L, and the kernel of this map has a filtration with subquotients delta L prime, where L prime is strictly bigger than L. And the second condition, delta L surjects onto L, and the kernel of this map has a filtration with subquotients L prime, where L prime is strictly smaller than L. So from this definition, it is very easy to see that an algebra A is quasi-hereditary if and only if its module category is a highest weight category, and in this case, deltas are exactly the standard modules. The advantage of the notion of a highest weight category is that a highest weight category might have infinitely many simple objects. And the relevant literature is a paper by Klein, Partial, and Scott, which is called Finite Dimensional Algebras and Highest Weight Categories. Let us now go back to category O. So let G be a semi-simple complex finite dimensional Lie algebra with a fixed triangular decomposition. Then we can consider the associated BGG category O. From what we now know about category O, we can claim that O is a highest weight category, where simples are indexed by elements in the dual space to the Cartan subalgebra. As a linear order, we can take any linear extension of the usual partial order on weights, so lambda is less than or equal to mu, if and only if mu minus lambda is a linear combination of positive roots with non-negative integer coefficients. And as deltas, we take the usual Verma modules. Similarly, for any parabolic subalgebra P of G, the corresponding parabolic category O is a highest weight category. So in particular, as a consequence, blocks of parabolic category O are module categories over quasi-hereditary algebras. Now let us discuss the notion of a tilting module. Theorem, which is due to Agoston, Happel, Lucas, and Unger from 2000, assumes that A is a standardly stratified algebra. Then, for any index I, there is a unique module Ti with the following properties. Ti is indecomposable. Ti has both a standard filtration and a proper costandard filtration, and the standard module delta I is a submodule of Ti such that the cokernel of this inclusion has a delta filtration. So the module Ti is usually called a tilting module for A, and the direct sum of all Ti's is usually called the characteristic tilting module for A. So here are some properties. First of all, the module T has finite projective dimension. Second, the module T is homologically orthogonal to itself. All extensions of strictly positive degrees from T to T vanish. And finally, the projective generator of A has a finite co-resolution by modules in the additive closure of T. The relevant literature for this theorem is a paper by Agoston, Happel, Lukács, and Unger called Standardly Stratified Algebras and Tilting from 2000. Let us now discuss the dual notion of cotilting modules. Assume that A is a properly stratified algebra. Then, For any index I, there is a unique module Ci with the following properties. Ci is indecomposable. Ci has both a proper standard and a costandard filtration. And the last property is that Ci surjects onto nabla I, such that the kernel of this map has a costandard filtration. Terminology Ci is called the Cotilting module, and the direct sum of all the Ci's is called the characteristic Cotilting module of A. And of course, Cotilting modules have properties which are dual to those of tilting modules. So C has finite injective dimension. C is homologically orthogonal to itself. All higher extensions from C to C vanish. And every injective cogenerator of A mod has a finite resolution by modules in the additive closure of C. In the case of quasi-hereditary algebras, since standard and proper standard modules coincide, and similarly costandard and proper costandard modules coincide, we get that if A is a quasi-hereditary algebra, then the characteristic tilting module is also a characteristic cotilting module. Please note that there exist properly stratified algebras which are not quasi-hereditary and which have a similar properties, that the characteristic tilting module is also cotilting. For quasi-hereditary algebras, the founding paper for tilting theory is a paper by Ringel, which is called The Category of Modules with Good Filtration over a Quasi-Hereditary Algebra, has almost split sequences from 1991. And because Ringel started this leads to the notion of Ringel duality. Let A be a basic quasi-hereditary algebra and T the characteristic tilting module for A. The Ringel dual of A is defined at the opposite of the endomorphism algebra of the characteristic tilting module for A. And the main statement about the Ringel dual is that the Ringel dual of A is a quasi-hereditary algebra, and taking the Ringel dual twice gives you an algebra which is isomorphic to the algebra you start with. And for this isomorphism, it was important that we assume that A is basic. Additional property is that taking homomorphism from a characteristic tilting module induces an equivalence between the category F nabla for the algebra A and the category F delta for the algebra, the Ringel dual of A. As a consequence of this equivalence, it follows that this functor hom T blank sends injective A modules, so they are relatively injective objects in this category, to tilting R of A modules. So these are relatively injective objects in this category. Since T is a tilting module, it's in particular a generalized tilting module, so the right derived of this functor hom T blank is an equivalence between the bounded derived category of A and the bounded derived category of R of A. And the paper of Agoston, Happel, Lukács, and Unger generalizes Ringel duality to the setting of standardly stratified algebras in the obvious way. Now let us go back to category O. First of all, let us show that the simple preserving duality on O commutes with projective functors. In other words, for any projective functor θ, there is an isomorphism of functors. Duality after θ is isomorphic to θ after duality. Of course, it is enough to prove that duality commutes with tensoring with finite dimensional modules, since projective functors are direct summands of tensorings with finite dimensional modules. Let V be a finite dimensional module and M be a module in O. Of course, we know that V dual is isomorphic to V because every finite dimensional module is semi-simple and the duality is simple preserving. Now, directly from the definitions, we have that the dual of V tensor over Cm is isomorphic to the dual of M tensor over C, the dual of V. Since the tensor product is commutative, this is isomorphic to the dual of V tensor over C, the dual of M. And since V is isomorphic to V dual, this is isomorphic to V tensor over C, the dual of M. And this completes the proof. Taking this into account, we can now construct tilting modules for category O. Let lambda be a regular integral and dominant weight. Denote by theta w the indecomposable projective functor from the block O lambda to itself, which sends the dominant projective module PE to the indecomposable projective module PW. Proposition: the module theta w applied to the simple Fermat module delta W0 has the following properties. First of all, it has a Fermat flag. Second of all, it is self-dual with respect to the simple preserving duality. Third, the highest weight of this module is W0 W dot lambda. And finally, this module is indecomposable. For the first claim, we know that projective functors preserve modules with Fermat flag. So for the second claim, we know that the duality commutes with projective functors, and since the module delta W0 is simple, it is self-dual. So the second claim follows directly. To track the highest weight, I leave as an exercise, and the claim about indecomposability will be proved later when we will talk about Ringel self-duality of category O. The notation, the module theta w applied to delta W0, is usually denoted by TW0W. And for singular blocks, we can take these modules which we construct in regular blocks and translate to the walls. And in this way, we get tilting modules for singular blocks. So here is an SL2 example. If we take the algebra SL2, then the while group consists just of two elements, the identity and the simple reflection S. If we consider the principal block of category O, then the indecomposable projectives in this block look as follows. So we have the dominant projective, which has its simple on top and the antidominant simple in the socle. And this is a standard module because it's dominant. And then the antidominant projective, which has the simple on top, and then the trivial module in the middle, and it's simple in the socle. And we see that the standard module for this projective is just a simple module, and that this projective has a standard filtration. And now the indecomposable tilting module then will be the simple Fermat module. So this is a tilting module more or less by definition. And the projective module PS will be a tilting module with highest weight E. This is the module theta S applied to S. So here is a more complicated example, the SL3 example. So if G is SL3, then the while group is a symmetric group on three letters. It consists of elements E, S, T, ST, TS, and W0, which is STS or TST. And the graded filtrations of standard modules in O0 look as follows. So we know that this is a multiplicity 1 case, so the graded filtrations are given by the Bruhat order on the while group. So the antidominant Fermat is simple. Then the Fermats for TS and ST have their simples on top and the antidominant guy in the socle. And then in the next layer, the Fermats for T and S have their simples on top. Then the lengths 2 elements in the second layer, and the socle is W0. And the dominant Fermat module, which is also projective, has LE on top. The second layer is S and T, and then the third layer STTS, and the last layer is W0. So now we can look at the graded filtrations of tilting modules in category O. The antidominant tilting module is simple. The next tilting module for the highest weight TS is obtained by applying the projective functor theta T to W0. So we get the module with Löwe length 3, W0 on top, TS in the middle, and W0 in the socle. So here we have the standard module TS W0, which sits in the bottom, and the standard module W0, which sits on top of it. So for ST, the situation is similar by swapping the roles of S and T. To get the tilting module for T, we need to apply the indecomposable projective functors of first theta T and then theta S. We get the module which has delta T in the bottom, then delta ST and delta TS put on top of it, and then delta W0 in the absolute top of the module. And then for the tilting module Ts, we just swap the roles of T and S. And finally, the tilting module with highest weight E coincides with the indecomposable projective module for the simple W0, because it coincides with theta W0 applied to delta W0. So this is the indecomposable projective cover of LW0, which we have already seen. It has a Verma filtration with each Verma appearing with multiplicity 1. The next claim is that tilting modules are unique. In the category O setup, this is due to Collingwood and Irving from '89. Note that this paper predates the paper of Ringel, which gives a general case of quasi-hereditary algebras. So the claim is, let T be an indecomposable and self-dual with respect to the simple preserving duality module with Verma flag in category O with highest weight W dot lambda. Then T is isomorphic to the module TW. Proof. Let us consider the short exact sequence delta W is a submodule of TW, and then we have the cokernel which has a delta filtration. Applying hom blank T to this short exact sequence and noticing that T has a nabla filtration, we get a short exact sequence because this functor is exact on modules with the delta flag. And from that short exact sequence, we get a homomorphism from TW to T, which is induced by the natural inclusion of delta W into T, which is given by the highest weight of T. And similarly, one gets a homomorphism from T to TW, the homomorphism in the other direction. So if we take the compositions of these, both on TW and on T, they are identities by construction on the component delta W, therefore they are not nilpotent. And since both were indecomposable modules, it follows that these compositions are isomorphisms. So these modules are isomorphic. The original paper of Collingwood and Irving is the paper A Decomposition Theorem for Certain Self-Dual Modules in Category O. So now we can talk about Ringel self-duality of blocks of O. The theorem, which is due to Zergin from '97, let lambda be a dominant weight and A lambda a basic algebra of O lambda. Then the Ringel dual of A lambda is isomorphic to A lambda. So here is the idea of the proof. Taking Zergel's combinatorial description into account, we may assume that lambda is integral. We can also assume that lambda is regular, and the general case can be handled using translation to the wall. Consider the short exact sequence delta W0 is a submodule of delta E, and we have some cokernel. Let's note that delta W0 is a simple module, it's a simple socle of delta E, and that LW0 has multiplicity 0 in the cokernel. Applying the indecomposable projective functor theta W gives a short exact sequence TW0W is a submodule of PW, and then the quotient is theta W applied to the cokernel. What we want to prove that the restriction from PW to TW0W induces for all x and y in W an isomorphism between the homomorphism from Px to Py and homomorphisms from TW0x to TW0y. This claim clearly implies this statement. Please note that this kind of proof doesn't work for the parabolic category O. In fact, blocks of parabolic category O are usually not Ringel self-dual, but they are Ringel dual to blocks of some other parabolic category. So let us discuss this restriction of homomorphisms from projectives to tiltings. The main observation is that the tilting module coincides with the trace of the projective injective module in the projective module. So let's recall that if we take a simple module which is not antidominant and apply to it any projective functor, in the outcome we cannot get the antidominant simple as a subquotient, simply because antidominant simples are exactly the simples with maximal possible Gelfand-Kirillov dimension. So Ly has a strictly smaller Gelfand-Kirillov dimension, and projective functors cannot increase it. So by adjunction from this, we get that the top of any tilting module is a sum of copies of LW0, because it is obtained by applying projective functor to LW0. So hence, in particular, it follows that the tilting module belongs to the trace of the projective-injective module in PW. And from the fact that the cokernel doesn't contain any LW0 and applying theta W, we cannot create any LW0, we obtain that the tilting module TW0W coincides with a trace of PW0 in PW. So consequence, the restriction from projectives to tiltings is well defined, because we can always restrict homomorphisms to a trace with respect to any module. Also note that this restriction is faithful, since the socle of the tilting module coincides with the socle of the projective module, because the latter just is a number of copies of LW0. Any projective has Verma flag, and any Verma has LW0 as a simple socle. So for singular blocks, we can translate the whole discussion to the wall, and we get that tilting modules again are exactly the traces of projective-injective modules in projective modules. So now let's discuss the fullness of the restriction. We just proved that the restriction is well defined and faithful. To prove Sergil's Ringel self-duality result, it remains to prove that this restriction is full. Consider Sergil's combinatorial functor V. And let's apply it to our short exact sequence. Tilting is a submodule of projective, and we have the cokernel. So V kills the cokernel because the cokernel doesn't have any subquotient of the form LW0. And V is an exact functor. So since it kills this third part, so it follows that V applied to TW0W is isomorphic to V applied to P. Since the top of any tilting module is just the sum of copies of LW0, Sergil's combinatorial functor, its homin from PW0, this is clearly full on tilting modules. And we know from Sergil's combinatorial description from his Struktursatz that V is full and faithful on projectives. Since V applied to tilting and to projective coincide, and it's full on both, it follows that the restriction from projective to team is a full functor. And the same argument works also for singular blocks. This in particular applies that the tilting module TW0W, which is theta W applied to delta W0, is indecomposable because its endomorphism algebra is isomorphic to the endomorphism algebra of PW, and the later one is a local algebra because PW is indecomposable. Okay, some questions for PhD students. Question number 1, show that an algebra is hereditary if and only if it is quasi-hereditary with respect to any choice of linear order on simple modules. Question number 2, prove that the regular block of category O is not a highest weight category with respect to the opposite of the usual partial order on weights. Question number 3, construct an example of a properly stratified algebra for which the characteristic tilting module is not cotilting. Question number 4, prove that W0W.lambda is the highest weight appearing in the support of theta W applied to delta W0. And finally, question number 5, write down with all details the proof of the claim that in all singular blocks, tilting modules coincide with the traces of projective-injective modules in projective modules. Thank you very much. See you next time.